it on the scale after they took off their backpack. And what I'm going to do is I'm going to go ahead and post up my weight. So my weight in high school is what I'm going to post. When I was in high school, not my current weight, but my weight in high school was 103.6. I know, that's what happens when you get older. So in high school, 103.6 was my weight. Now, here, I like to go ahead and always remind you, hey guys, if there's an equation that is not on the formula chart, let me highlight it. This equation is not on the formula chart. So you might want to highlight it. You might want to write a little note, not on formula chart. What do you mean, Miss Munson? Well, what I mean is, in the medical field, for an example, you go to the doctor's office, you stand on the scale, and it says 172 or something. Okay, not a problem. The doctor or the nurse has to convert that number into kilograms because medicine is in a science field, and they have to go by the metric system. All medication, all shots are all within the metric system. So if that's how much with your calculator, write down your number when you stood on the scale. I need you to convert it into kilograms. Now to do that, we're going to go ahead and get your number, get your personal number, divide by 2.2. It is a memorized equation. How do I convert from pounds to kilograms? I divide by 2.2. So now write your new number in, 47.09. That for me, write your personal number in. Write your own number. Don't write my number because when I grade your notes, I need your own personal number. That's how much mass I am. And remember, the word mass means stuff. So, as a quick reminder, we had, oh, here it is. Forgive me. I would be prepared for the quiz next week. Do you recall this question that we went over in class yesterday? What if, look at this. Do you see how they have him as 48 kilograms and that girl has 40 kilograms? What if it was in pounds next week on Tuesday?
Multiply by 2.2.
Divide.
Divide by 2.2.
Divide by 2.2. Divide by 2.2. Mm-hmm.
But we're converting kilograms to pounds.
Oh, I'm so sorry. I would never, yeah, if I need you, thank you. If you need to convert to pounds, you would multiply by 2.2. But if their number was 143 and 103 pounds, you would need to convert by dividing by 2.2. That's what I was trying to say. I'm so sorry if I misquote. So be prepared on Tuesday that this number, there's a good chance, may not be in kilograms. It may be in pounds. And we know now, how do we get to pounds? From pounds to kilograms, we divide by 2.2. Let's keep going. So with your calculator, it says here, well, what is your weight? Please don't forget, the word weight means gravity, or your brain needs to think gravity. Okay, so if it's about the gravity, gravity changes when you go from one object to another, like as in Earth to the moon. But gravity also changes. Here, we live in Galveston County. We are at or below sea level. If you were to go to Colorado mountains, then the gravity would change because you're further away from Earth. So if gravity was to change, then your weight would change. Not, I stood on the scale weight. No, that is how everyday normal people use the word. In physics, the word weight is due to gravity. So let's go ahead and write that kilograms down, put your personal number. Now we're going to multiply it by the gravity's number, which is here on Earth, 9.81. And I do want to mention, because I said this earlier today, one thing in physics that we can assume is that we are always on Earth, unless they tell you otherwise. Okay, so I multiplied it by 9.81. They did say on letter B, I'm on Earth. But if they don't say it, we can assume that we are on Earth. Now, we're going to go ahead. It says here, you're going to the moon. So all of this is on Earth. Now we are on the moon. And so it says, let's go ahead and find your weight. Again, the word weight means gravity. So I'm going to get my mass of 47.09. Oops, 47.09. I'm going to multiply it by, well, I know gravity here on Earth is 9.81, but the moon is actually 6 times smaller. So that's the reason why it says divide by 6. So if I have my weight on Earth, if I divide it by 6, because now we're on the moon, my weight on the moon is 76.99 newtons. Okay, so let's pause for a moment. You stood on the scale, and when you stand on the scale, you get your pounds. Okay, we don't speak pounds in physics. We speak kilograms. And so we convert it from pounds to kilograms. Then, stop and think for a moment. You are sitting on that chair. As your butt sits on that chair, your body, your butt is exerting a force on that chair, on Earth. This is the number that your body is exerting. Some of us are exerting 500, 600 newtons of force on that chair. But if we were to take the same chair and the same you to the moon, where the moon is 6 times smaller, then you would only exert 76.99 newtons on that chair. Less force on that chair. Why? Because there's less gravity. And then the last part, let's go back. We stood on the scale again. Divide by 2.2 to figure out what would our mass on the moon be, and it would be the same exact number. And the reason for that is because your mass is always going to stay the same. Your mass is never going to change. It says here, hopefully you notice between these numbers here that your weight changes and that your mass always stays the same. Yes, sir.
So mass would be in kilograms and weight would be in newtons?
Yes, yes. I would, yeah, for anybody who needs to write that down, that would be a really good little, I'll put a star here. Weight in physics is always going to be in newtons, and mass in physics is always going to be in kilograms. If they give you the number in grams, you must convert to kilograms. Oh, that's a really good way just to simplify it. It says here, because your body will always contain the same amount of stuff. Remember, I gave the example, unless you get both legs cut off, the amount of matter you have is the amount of matter you have. Now, we're going to move on to the last section of our notes, and then we are good for the day, and we're good for our notes. Please go back over the weekend and see what you're missing so you can fill it in. Newton came up with what he calls the universal law of gravity, or he says the word universe actually refers to everything. Like everything, the moon, the sun, the planets, you, a rock, everything. And the law of universal gravitation, it says here, states that all objects in the universe that has mass will exert a gravitational force on other things. Now it says the strength of how strong that gravitational pull is between any two objects depends on two things. Number one, their mass, and number two, the distance they are between each other. So it says here, for an example, the bigger the mass, the stronger the force, or the closer those two objects are to each other, the stronger that gravitational force is. For an example, have you ever walked down the hallway and you weren't necessarily like trying to, ram into somebody, but before you know it, you either hit the wall or you bumped into somebody. It's just that natural gravitational force you have to another object. The closer you are, the gravitational force becomes stronger. Okay, it says here though, remember Newton's third law says for every action there is an equal and opposite reaction. This means that object number 1 pulls on object 2 with the same amount of force as object number 2 pulls to object number 1. They are equal and opposite.
Wouldn't that mean that the pulling force on both of them would be double, or would they cancel out?
They would cancel out. But the object that has less mass, if these two objects were like colliding or ramming into each other, that would be like when we get to our next unit, momentum, it would cause the one with less mass to maybe fall back. Like if you were to go and run football game, there you go, 2 football players, the one that is the less mass is probably going to fall back further or move back further because of that. But the force between them at that moment will be the same, equal and opposite to cancel out. The last portion here, I might be wrong, is the math equation in practice. Like I said, we're not too much more of notes, and then we are done with this unit. To fill in?
To turn it.
Oh no, it's not going to be. It's not going to be until next week.
Okay.
Unless it's due. Is it already available? I don't know. I thought it wasn't until next week. I would have to check. I wanted to make sure. Again, most equations I try to put a box. I apologize. I did not give you a box for this equation. Again, that's a memorized equation. This equation, which is what we did in our lab earlier this week, is the gravitational force equation from Newton says that G, or big G, times M1 times M2 divided by distance square. Now I'm going to write this word over here, or sometimes you can see this equation written as FG equals big G M1 M2 divided by R squared. Now, we in our notes, when we did, in our lab, we had R squared. R squared and D squared are the same thing. No, they're not, Ms. Munson. R stands for radius, like of a circle. I get you. Newton, even though he knows not all objects are round or a circle, but all objects still have a center point, or center of gravity, the center of gravity of that object. So here's what I want to make sure I tell the students today. For an example, the distance of the center, or that core of that center. I would be prepared, if I was you, for next week. What if this is a marble and that's a marble? I gave you the mass of marble 1 and the mass of marble 2. And then I give you a ruler. Pretend here's my ruler. Here's the ruler. You need to take the measurement. You are going to measure with the ruler from the core or the center of that object to the core center of that object. And that's where Newton came up with the R square, radius. Or again, you can call it distance, but it's going to be from the center of this object to the center of that object. Oh, wait a minute. Distance. Distance should be, D stands for distance, or R. Distance between, two ends. The two objects should always, 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 always be in meters. Well, obviously I'm going to give you a ruler that has centimeters. So it's going to be your job to remember to convert it to meters. Okay? You got to remember that. You got to remember that. F stands for force of gravity, Fg, which is in newtons. That big G is his constant. Gravitation constant. And earlier today, I think I put it back up. Maybe, let me see. Earlier today, I pulled out the formula chart. Here it is. And I told the students, don't freak out. Next week on Tuesday, here it is. Right there. 6.67 times 10 to the negative 11. So 6.67 times 10 to the negative 11th power. Okay? It's a constant number, and it's already here. You don't have to freak out. M1 is the mass of object number 1. Which one is 1, Ms. Munson? You make a choice, and you call it 1. M2 is the mass of object number 2. And if I give you the mass, what if I don't even give you the mass? What if I say, here it is, go to the scale, and the scale gives it to you in grams, convert to kilograms. If I give it to you in pounds, convert it to kilograms. But this must always be in kilograms. No ifs, ands, or buts on that. Alrighty? One more thing before we do the practice problem. Here in the formula chart, I don't want anyone to freak out because sometimes it gets overwhelming taking your quiz and test. But here is the actual equation. Force equals big G times M1 times M2 divided by the distance squared, or R squared, whatever you want to call it. So moving that out the way, let's do a practice problem. It says here, let's find the gravitational force between Earth, M1, and the Moon, M2. And the distance between them is, my commas are messed up. So let's go ahead and I'm going to write my equation. Force equals G M1 M2 over distance squared. Or I'm looking for force equals 6.67 times 10 to the negative 11th times the mass of Earth, which 5.97 times 10 to the 24th, multiplied by the mass of the Moon, 7.35 times 10 to the 22nd power, over the distance, 3,844, 0.0000000. But don't forget to square it. You absolutely can put this into the calculator in one shot, but I like to do it in 2 different steps just to help make sure. I squared this bottom number and I got 1.48 times 10 to the 19th. And my answer times 10 to the 8th, the unit is Newton. Gravitational force is a Newton. Hopefully not too bad. Turn the page. All I'm going to do is set it up. I'm not going to do anything. We're not going to do it. I'm just going to set it up. You can do the math later on. I'm going to come over here and I'm going to do this middle one. It says, what's the gravitational force between Sam and Ashton? So question mark FG. If Ashton has a mass of M1, Sam has a mass of M2, while they are standing 3 meters apart distance. So for this situation, back to that same equation, Fg equals big G M1 M2 over the distance squared, or that constant number, 6.67 times 10 to the negative 11th, multiply by Ashton's mass of 83. So what I wanted to say is not all masses are crazy big numbers. They can be regular numbers, 101. They are in kilograms, so we're good there. We don't have to convert anything. 3 squared. And see, we can have little numbers that are just not so astronomically big. And then go ahead, don't forget to square the 3 and multiply everything and then divide it by your 9 at the bottom. Not bad, easy cheesy. The next one is we've got 2 billiard balls, but they show me that they have 2 different masses and the distance between them is 1/2 meter. Look for the force. Or force equals gravitational constant, 6.67, times 10 to the negative 11, times M1, M2, over the distance squared. Again, sometimes we can have small decimal points as numbers. They don't have to be crazy big numbers. Again, all you have to do is finish the math part, but our notes are done. Unit 2 notes are done. Please bring your Penny Lab next week. We will do that